Welcome to SA108. We're going to discuss the communication physically between a remote terminal unit and the control center. We will start by talking about the serial communication, what is the common standard, how it's used. In the same sense, we will talk about the Ethernet communication. Then we will cover the radio communication. And next, we will cover the modem leased line communication. Finally, we'll talk about the JungleMux, where a lot of mediums get merged together into a single pipeline. Okay, so let's start with serial communication. So the objective of a data communication system in a utility is to transfer data, information about the switch yard to the control center via a remote terminal unit. The information in the switch yard has to first be digitized so that it can transfer via a physical medium. And in the remote terminal unit, it gets concentrated and formatted in a way that the control center wants to look at it. And then it's put on a medium, on a physical medium that's allowed in the local area regulations. If we have more than one option with the local area regulations, like we could transmit it via serial network or leased line, then we have to make a decision about what bandwidth are we looking at, what is the best investment, return on investment that can take place. So the aim of this overview is just to show you the different mediums, the capacity of the different mediums, and is the decision making around the medium for transmission of data. The most common example of a broadband medium for information transfer is the coaxial cable. It allows for greater throughput with lower error rates. Also, by its design, the coaxial shielding reduces noise interference to a greater degree than the twisted pair design. Coax can carry many different channels of information at the same time. It can be used for up to 2 gigahertz, but can support up to 10 gigahertz. So as you can see, the DTE and DCE setup between transmitter and the receiver. In the parallel conductor, we can send data and receive data and use all the data signals for transmission. The medium, the parallel medium, would be used to as an encoding of the character, so the character will get encoded similar to a serial communication. So in both parallel and serial, we would encode a character into bits that's traveling along the wires. The difference is in parallel, you will use all the conductors. In the serial, you will use only 2 lines, which is transmit and receive line. So the idea is we capture the data and then encode it either for parallel, where we use more conductors, or as serial, where we use only 2 lines for transmit and receive. Serial communication has its limitation of speed. For example, synchronous is meant for sending clock with the data versus an asynchronous communication. One of the protocols that's available is the RS-232, which is the most common. But there is other protocols like the RS-422, RS-423A, RS-449, RS-530, RS-366, and so on. The DTA, or the data terminal equipment, for example, would communicate over a serial port, yet the DCE, or the data communication equipment, has an example of a modem, which would transmit the data that's received from the DTE. You can also, under serial, communicate with a video display terminal for a monitor, where you would show the data. The RS-232 standard defines the electrical characteristics and timing of signals, the meaning of the signals, and the physical size and pinouts of the connectors. The RS-232 serial port was once a standard feature of a personal computer. You used to walk into any store and buy an RS-232 cable that's a 9-pin serial cable, or a 25-pin. That was very common everywhere. and it was used for connection to modems, printers, mice, data storage, uninterruptible power supplies, and other peripheral devices. However, the RS-232 is hampered by low transmission speed, large voltage swings, and large standard connectors. In a modem personal computer, the USB has displaced the RS-232 standard for most of the peripheral interfaces. Nevertheless, the RS-232 devices are still used in substations. We still find them even after all of this time, and there is a lot of industrial machines that depend on the RS-232 communication and connectors. Okay, so let's talk about capacity, bandwidth, and noise. Basically, capacity is proportionate to bandwidth, and noise reduces the capacity. The more the frequency of a signal, the more is achievable from a data rate or information transfer rate. In general, we say capacity is equal to bandwidth multiplied by log of 1 plus power divided by the noise. The signal bandwidth of transmitted line is a single is known as the single bandwidth. Channel bandwidth is the range of a signal bandwidth allowed by the communication channel without any loss of data. Channel capacity is the maximum rate, bits per second, at which data can be transmitted over a common link or channel. In order to understand the channel capacity, we must first look at the bandwidth. Notice the capacity is proportionate to the bandwidth. And next we look at the physical link, or the channel that's used for communication. And there is, once we're looking at a signal, we can tell the difference between a good signal to noise ratio versus a bad signal to noise ratio. Okay, so as we said, the data has to be first digitized, so it has to be put into digital. So we take changing data and put it in a digital format, basically bits, ones and zeros. And once we put it in a digital value, then it has to be multiplexed either over time or over a frequency. When we multiplex it, there is many different types, so it can be either time division multiplexing, TDM, or frequency division multiplexing, FDM. And there is also pulse coded modulation, PCM. Okay. Basically, when we're transmitting data, there is two factors, bandwidth and noise. And bandwidth is the range of electronic, optical, or electromagnetic frequencies that can be used to transmit a signal. Noise is anything that can disturb the transmission of a signal. Over the years, the digital signal has been characterized based on the amount of megabits per second that it can transmit. So we've got a DS1 which can do 1.5 megabits per second. We've got a DS2 which can do 6.3 megabits per second. A DS3 can do 44.7 megabits per second, up to a DS4 which can do up to 274.1 megabits per second. So it makes sense that the technology keeps going forward. We need faster way to communicate data. So the copper wire wasn't sufficient to handle higher and higher rates, was always susceptible to noise. So as such, the fiber optic technology is a good alternative. It can handle high capacity, has a high frequency, it is very economical, has low loss of signals. It's free of interference, does not radiate energy. It comes in two modes. Of course, there is the multi-mode and the single mode, and that talks about how the light is sent through the fiber cable. In the old days, it used to be very expensive to implement fiber cables in substations because the technology was new. The tools used to cut the fiber and terminate it were new tools that were not perfected. With the perfection of the tools and the usage of these cables and the termination of these cables, now it's very common to find fiber in a substation. An example is the brick, the GE Multilin hard fiber, which sits at the switchyard. It collects data directly from all the copper cables, so this way you don't have to send those copper cables in conduits all the way to the control room. Instead, you just send one fiber cable from the switchyard all the way to the control room or the relay room, and then that fiber is connected to the relay or the concentrator, and data can then be transmitted to the control center. So after serial comes the LAN, or the local area network, which is a data communication facility located within a single building or campus, which provides all high-speed switch connections to its terminal, processors, and peripheral devices. Originally, it was a proprietary protocol that was created to communicate with multiple devices, media similar to the serial copper fiber radio. There was a need for standardization. So came the ISO model, and with the ISO model you could transmit up to 10, 100, and 1000 megabits per second. And then the standards started to show up for the local area network, which allow for this switched communication and allow for high-speed communication, unlike the serial and the parallel communication. And data was transmitted at, for example, then one of the standards that show up was the 802.1, which is the OSI level coordination. And then you've got all the different types of the 802. So you've got the 802.2, which is the logical data link, and .3 was the Ethernet, the .4 was the token bus standard, and .5 was a token ring standard. And the layout of the network was up to the implementer based on his knowledge of which is more reliable, which is within the reachable technology, in order to implement either a ring or a bus architecture. The early implementation of network was based on basically a coax with various grades. Later came the shielded twisted pair, and simple unshielded twisted pair using a Cat3 cable. The same simple cable can be used for like a telephone system, category 3 cable, or a station wire is unshielded twisted pair used for telephone wiring. Okay, so we talked about the OSI layer. Basically, the layers of the OSI allow for each application to have a specific functionality that can be executed separate from the next layer, and what each layer does becomes the load for the next layer, and the next layer will add its extra packets and create the load for the next layer, and so on. So for example, as you can see, we've got the user application layer, and then you've got an application layer that creates the user data payload, and then the payload will get more information attached to it. So let's say if it is DMP, and the DMP message has to start with 0564, maybe that will be added to the message at that layer, and then the presentation layer will make sure that the information is ready for transmission, the session layer will establish a session with the other device and make the session, and so on. Each layer has its own specific functionality where it would add to the message and then pass the packet to the next message all the way to the physical layer. That's where the transmission will take place. For radio communication, by convention, it is between 3 megahertz and 30 megahertz. Can be transmitted via ground wave or a sky wave bounce between ground and the ionosphere. The high frequency is the RTU, which stands for the International Telecommunication Union designation. For the range of radio frequency, electromagnetic waves, basically radio waves, between 3 and 30 megahertz. Basically, it consists of a transmitter station and a receiving station. The satellite orbits about 25 kilomiles from the station. The station sends to a transponder per satellite. In turn, the transponder transmits to a receiving station. So WiMAX, or the Worldwide Interoperability for Microwave Access, is a family of wireless communication standards based on the IEEE 802.16 set of standards, which provide multiple physical layers and media access control options. How it works, WiMAX has the potential to do broadband internet access, basically what cellular phones have done to the phone's access. In the same way that many people have given up their landline in favor of cellular phones, WiMAX could replace the cable and DSL service, providing universal internet access just about anywhere you go. WiMAX will also be as painless as the Wi-Fi. Turning your computer on will automatically connect to the closest available WiMAX antenna. In practical terms, WiMAX would operate similar to Wi-Fi, but at a higher speed, over a greater distance, and for a greater number of users. WiMAX could potentially erase the suburban and rural blackout areas that currently have no broadband access because the phone and cable companies have not yet run the necessary wires to these remote locations. Basically consists of two parts. There is the WiMAX tower and the WiMAX receiver. The WiMAX tower, similar concept to the cellular phone tower. A single WiMAX tower can provide a coverage for a very large area as big as 3,000 square miles, approximately 8,000 kilometers. The receiver and the antenna could be a small box, any small dongle or PCMCIA card that you could connect to and built into your Wi-Fi, similar to how you connect Wi-Fi today from a laptop. A WiMAX tower station can connect directly to the internet using high bandwidth wired connection, for example, like a T3 line. It also can connect to another WiMAX tower using a line-of-sight microwave connection. This connection to a second tower, often referred to as a backhaul, along with the ability of a single tower to cover up to 3,000 square miles, is what allows the WiMAX to be able to provide coverage for remote rural areas. This was a quick overview. WiMAX subject is a little bit bigger and more intensive. There is lots of literature on the WiMAX and how to set it up. So a microwave radio will allow us to set it up at like a substation by a line-of-sight carrier system to carry large quantities of voice and data signals, range from 1.7 to 19.3 gigahertz, transmit both digital and analog signals. One of the common questions is why wireless communication? The use of wireless transmission carries many benefits. User can control the media. The user have a lot of control over the media and the setup. Speed and ease of installation with no cabling to run between stations. This will ease the lease issues and the renting issues and the real estate issues. Excellent throughput and speed and security and reliability as technology is improving is all paying off toward the ease of installing a wireless radio communication system. So a private line, or a digital private line, sometimes referred to as DPL, in a wired telephony system, is a service that involves a dedicated circuit, a private switching arrangement, and or a predefined transmission passes, whether virtual or physical, which provide a communication between specific locations. Most private lines connected only to two locations, though they might be switched at either end or both. Some have multiple drop points. In areas where regulation allows utilities to install their own communication lines, private lines are installed. In some cases, these lines are run with a transmission line that's running between stations. These lines are not linked by any shared public switched telephone network. Improves the security and the control over communication for a utility to have its own private communication. So a leased line service or a private line service became digital in the year 1970. A leased line is a private bidirectional or symmetrical telecommunication between two or more locations provided in exchange for a monthly rent, sometimes known as a private circuit or a data line. Unlike traditional PSTN line, it does not have a telephone number, each side of the line being permanently connected to the other line. These lines can be used for telephone, data, and or internet service. Some are ring down service, and some connect to a private branch exchange. So typically the older stations communicate involved using public switched telephone network. Later the need for a private constant connection requirement became greater. A private line with bidirectional telecommunication was available between basically two locations. Finally, we'll talk about the JungleMux device, which allows you for carrying of multiple packets such as data, voice, movie streams, etc. Over the same communication line. For example, the electronic JungleMux have the ability to eliminate the need for complex multi-device equipment, seamless capacity to upgrade from an OC1 to OC48, system availability with redundant common equipment for path switched ring networks, fast path protection switching, reduced connectivity, expansion and configuration costs through modular design, advanced network visibility from SONET level down to individual DSO signals, advanced network availability for SONET level down to individual DSO signals, comprehensive network management capabilities using FistaNet, and secure and independent transport for critical services. Whether it's DSO, a digital signal zero, is a basic digital signal rate of 64 kilobit per second. And by the way, VistaNet is a suite of software tools that manage the GE Electronics telecommunication system. Thank you for taking the time to watch this overview of physical available connectivity between the remote terminal unit and the control centers. Obviously, as technology advances, there will be more options. Today, we have seen the many choices of transmission media, the coax, the wireless, the data, and the voice. And there is a lot of efforts in the substations right now to not only monitor the data, but also have visual inside the substation. So cameras will be installed inside the substation, and data is transmitted using the available media, not only SCADA data, but also video data all the way to the control center. In case there is an issue, there is an ability to connect to the substation and monitor everything in the substation remotely. The most important thing to remember is that the decision of the media depends on the regulations and the availability of the technology. And that's at all levels. So different technology levels, the wiring, the receiver, the sender box, all of these have to be available for a long time and maintainable, which is a key thing. One of the key thing is not just to think about the availability of a technology, but what's about the maintainability of the technology. How long will that manufacturer that's manufacturing this technology be around in order to support long-term maintenance of your communication. Remember, this communication, once it goes in, the expectation of a telecommunication company is that it will last at least 20 to 25 years. Everything plays game when you make that decision, the cost, the distance, the bandwidth, and it's a balance. So you have to reach a balance between cost, distance, and bandwidth. If you have high speed, but you really don't need all of that bandwidth, then you might have overspent the cost of building this communication system. So the idea is that you have to make a balance between what is required, how much of it is real data that is really required at the control center, and how much of the data can be left at the remote substation for service. All the best. See you in future trainings.